Okay, so I want to start with kind of just a hypothetical question. I know yours aren't in color, but you can see the ones on the board. How are these functions related to each other, is my question. And at first, let's maybe just talk about what type of functions we have. What categorize the red function for me? What kind of function is it? That's quadratic. Everybody okay with that? Okay. And then the light blue function is also quadratic, whereas the dark blue function is linear. We're all good with that terminology? Okay. So one of the things I need to work with you guys then is more on function operations. And I brought this up yesterday a little bit, the idea of can we add, subtract, multiply, and divide functions from each other? Right? Now, dividing is what we really focused on yesterday, but you guys have already learned multiply, because multiply is really FOIL, right? And add and subtract, really you just combine like terms. So if I use that as a bit of a clue, I'd like for you guys to try to consider how does the two blue functions combine to give you the red function? How do the two blue functions combine to give you the red function? And Darian, you say? Yeah. Look at that. Take this function right here, x squared. What if you added it to 2x plus 1? Well, x squared doesn't have any other terms but the x squared, right? The 2x plus 1 doesn't have an x squared term. When you add them together, you get the other red function. What I'd like to do is actually approach this from a few different ways of looking at it. You could then state that g of x plus f of x equals h of x. You guys agree with me that's a true statement? Right? I mean, the reason why is that if you wanted to write it out, this is 2x plus 1, this is x squared, and so, yeah, of course they equal x squared plus 2x plus 1. It's just a slightly different order I wrote them in. I'm going to close that door. Well, we can approach this from a few different ways. I need to teach you guys how to consider graphs, which is what I just drew right here, right? I also need you to consider equations, because you could add equations. Right? Here, I was literally adding equations. Over here, I'm adding graphs. Another thing I could do is I could add like a table of values. Let me show you how this might look a little bit further below. If I were to write a table of values that looks something like this, I'm going to give you, this is going to be what x is. This is going to be what f of x is. This is going to be what g of x is. And what was the other letter we used? H of x. Okay, let's pick a value for x to look at. Probably the easiest one to do is like 1 or 0 or something like that. So why don't I start with x being 1? If x is 1, which means that I'm looking like along this vertical stripe, you guys get what I mean there? That's where x is 1. What is f of x? Well, f of x was the blue one. The blue one was at 2. No, 3. Agreement on that? So when x is 1, this one is 3. Well, when x is 1, what's g of x? G of x was the light blue one, right? When x is 1 right here, what's g of x's value? Also 1, yeah, because you can see how the coordinate point right there is 1. And then for the last little bit, what's h of x's point? Well, it's up here at 4. And what did we think our equation was? It was f of x plus g of x equals h of x. Is 3 plus 1 equal to 4? Yeah, it is. Now, that can't hold for just when x is 1. That has to hold for literally every single x value in the universe. Now, I don't want to do this for every single value. That's impossible, right? But let's just check one more. Why don't we try it for when x was 2? And just make sure that it works. So, back up here, f of x, when it was 2, is a 5. G of x, when it's 2, is a 4. Now, is h of x actually on the red graph that I can actually see? Actually, it is, isn't it? Isn't it right there? Which is at 9. Doesn't that make all the sense in the world? Because isn't 5 plus 4 going to equal 9? So I need to show you that we need to be able to add functions in multiple different ways. And that's the title of our lesson, right? We're going to talk about function operations. So the main operations are add, subtract, multiply, divide. But we need to be able to work with functions in multiple formats. Graphical format, table of values format, equation format. Sound good so far? Most of the time, you guys have really only been asked to add or multiply equations in this format here. What's x plus 2 times x minus 2? And so you guys have learned the really good algebra skills of saying, well, this will give you x squared minus 4. But I need you to be able to do that with a graph or with a table as well. Sound good? Let me move forward here. I think you got the point of our lesson. Here's a couple of ways that we can notate things. If we ever want to add or subtract functions, a couple of ways we might show them is f of x plus g of x, or you might see it like this, in brackets f plus g, bracket x. All this means right here is just add the y values. Before I go further, I need to make sure, when I say this right here, I call it g of x. Have I shown you guys and used that vocabulary before? Or did I gloss over that too much? You're nodding at me. You're okay with that? Okay. All that means is that this is an equation. Right? A lot of times we write it as y equals something, but what if we want more than one equation? Well, we often go f of x is the first equation, g of x is the second equation, m of x is the third equation. It's a nice way to keep them straight. Because if you tried to go with y1 and y2 like your calculator does, that's a little confusing. Okay. So anyways, I need you to be familiar that if you ever see f minus g in bracket of x, all it means to do is take your two equations and subtract them. Or another thing it means is take all of the y values and subtract them from each other. So let's try another example here. I'm going to give you the graph of 2x minus 1 and the graph of x minus 2. And I want to quick sketch both of those graphs, and then I want to see what happens when we add them to each other. So, do you guys know how to sketch a graph of x minus 1 2x minus 1 really quick, right? Like, give it a y-intercept of -1, give it a slope of 2, and that should more or less work. Like, don't take 10 minutes to make it perfect. That's our graph. Does that work? And then I'll use another color because I can. If you guys have another color, you could. If not, don't stress it too much. X minus 2 is going to be down here with a y-intercept of 2, and it's going to have a slope of 1. So it's going to look something like this. Give or take. So let's try adding these together visually from what we see from the graph. So let me give you an example here. I'm now going to use a third color and add them together. The third color for me will be purple. Where would be a good x value to start with? 0 is great, yeah, like right here. Here's an x value of -1. Here's an x value of -2. What happens when you add a -1 to a -2? It's -3. I'll put it right there. And you more or less just do this for every single x value that you can. Right? So you just kind of work your way along. So let's do x as 1. Here, I believe one of them is at 1 and one's at -1. So when you add a 1 to a -1, it should give you a 0. That makes sense? Here, there's a 1 for a y value. Here, there's a -1 for a y value. When you add your y value of 1 and -1 together, it's 0. All right, here when x is 2, we've got a 0 and a 3. So 0 and 3 is 3. I'll just do one more and I'll call it a day. For a consistent x value of 3, we've got a 1 and I believe a 5. So 1 and 5 means this should go up here at 6. What kind of function did our product, no, product's the wrong word, what, the sum of these two things? How do you categorize this purple line here? What kind of function is it? Yeah, it's still linear. Does that make sense from an equation point of view? We just did a graphical point of view. From an equation point of view, 2x minus 1 plus x minus 2, well, it would give you 3x minus 3. 3x minus 3 is still linear, so that makes sense, right? Does this graph meet the properties of a 3x minus 3 graph? Well, yeah, the y-intercept is down here at minus 3, and as I look at it, the slope sure looks like it's 3, so that fits. Does this concept make sense? Okay. So basically what I need to do now is just show you a whole bunch of different ways in which we can use these skills for add, subtract, multiply, divide. Obviously, add looks pretty simple. This one here involves subtract, but in the interest of time, do you guys feel like you could handle subtract? Let's move on. Let's try this one here. I know it skips a couple of graphs ahead, but let's do a more challenging one. Let's hop down to the one where they need to multiply. What happens if I need to multiply f of x by g of x? So why don't we start by just doing that every point consistently again, right? So let's start over here with negative 4, and let's multiply the y values. For a consistent x input of negative 4, we've got a 1 and a negative 3. Multiply them. 1 times negative 3 will be, okay, so just keep it in this location right here. Then for a consistent x input of negative 3, you've got a negative 2 and a 0. Multiply those by each other, you've got 0. Okay. Now we've got two values right here that are right on the same mark, right? They're both at negative 1. Negative 1 by negative 1 gives you positive 1. Right off the bat, is this going to be a linear function? Because there's not a consistent slope, right? Let's play it out and see how it goes. 0 times negative 2 will be 0. 1 and negative 3 will be negative 3. 2 and negative 4 will be negative 8. And I'm more or less running out of room now. What did I just draw? You're quadratic. I mean, if I could keep going this way here, I'm sure it looks like that, right? Now let's talk about whether that makes sense, not just from a graphical point of view, but from an algebraic equation point of view. I didn't actually tell you what these equations were, but I don't think it's an unreasonable expectation that you guys should be able to tell me what the equations are, right? This top one is going to be x plus 1. Can you guys handle that? The slope is 1, and the y-intercept is 1. And this one down here looks like it is negative x minus 3, I think. Right, because it's got a slope of negative 1 and a y-intercept of negative 3. Okay, well, let's try this from an algebraic point of view. If I gave you x plus 1, and I gave you negative x minus 3, and I asked you to multiply them, you've learned this before, right? This is foiling, essentially. So foil it out. Negative x squared minus x minus 3x minus 3. You now have an equation of negative x squared minus 4x minus 3. That is, we would call that f times g of x. That would be a good way of notating it. F and g of x have been multiplied by each other, and this would be the equation we got. Well, this is quadratic, right? Our picture was quadratic. In terms of other properties we know, doesn't this negative right here mean the graph is upside down? We have an upside down graph. Doesn't this minus 3 right here mean our y-intercept is minus 3? And going back to the graph, y-intercept is minus 3. For the final equation here, negative x squared minus 4x minus 3. That makes sense to you guys? So for the most part, most people don't overly struggle with add, subtract, multiply, divide, or sorry, add, subtract, multiply. It's a weird way of thinking of things, because I've never really shown you it in this way, but really, this is now the culmination of years worth of skills, right? You guys have learned how to graph in 1 year. You've learned how to add variables to each other, like when you learned basic algebra. In grade 10 and 11, you spent a lot of time learning how to FOIL. The one skill that you're probably not as good at then, dividing. Fair enough? Right, like the add, subtract, multiply aren't the hardest ones, but divide sucks. So, why don't I skip this one here, unless you guys really feel like we need to do the exact same thing, but what do you think is going to happen when you times an x graph by a negative 2x plus 2 graph? What's the result going to be? Yeah, a quadratic. Okay. So You guys can probably handle that. So here's a way that you can deal with products. You can either write f of x literally next to g of x, or you can do f dot g of x, meaning that you're multiplying them. What I want to focus on for the next little while now is kind of what yesterday's lesson also helped lead us into. What if we're dividing? Some things divide nicely, right? Some things like, say, 10 divides by 2. 10 does not divide by 3. So it means I need to show you two different scenarios. Scenario 1, what happens if things actually do divide by each other? Right? 10 divides by 2 gives you 5, whole numbers. But the other possibility is, what if you try to divide it by 3 and you get 3.3 repeating? How do we deal with that scenario? You get what I'm saying here? So let me start with whatever example I have. Yeah, let's use this example here. What if I were to give you this function here and this function here? And let's start with multiply just because it's the first one on here still. I know I want to get to divide in a second, but how would you multiply these in equation format? What am I really asking to do? Yeah, FOIL. So you guys know how to do this, right? If I haven't done this with you guys in a while, here's one method I like to do. I'll go x times x squared to give you x to the third, and I put that in its own set of columns. Then when I go x times 4x to give me 4x squared, that goes in a column here. And then this one by this one will give me 3x. And then when I do it the other way, when I go like minus 2 times x squared, I would put that here and I go minus 2x squared, and I write it like underneath it, just because I like to keep my like terms together. And then when I do minus 2 times 4x, I would get minus 8x. I'm going to write it underneath this guy so they're together. And then when I do minus 2 times 3, I'm going to get a minus 6. I might write that there. I know this seems really like simple, but I prefer that to writing it like this. You guys see how I could put them all in one big row? When you're foiling out like large amounts of numbers all in a row, if you write them all in a row, I find that there's more likely a chance that you'll miss combining the like terms later. But if I write them so that like this one goes below the other like terms, I don't know, this is just a hint that I would give. Do you see how it makes it easier to see how to combine them? So your final answer will be x to the 3. You'll need 2x squared minus 5x minus 6. Does that make sense to you guys? Okay. So for the most part, up till yesterday in your math careers, you guys would have had the ability to take polynomials and make them bigger, make them into larger, like quadratic and linear makes you a cubic. Yesterday, though, I started giving you guys tools to break them backwards, right? Because if I wanted you to take a cubic or a quartic and make it smaller again, that's where synthetic division concepts come in. We're going to focus on that more in a couple of days. For right now, I'm probably going to keep everything to quadratics and smaller, just to keep things simple to start with. But hopefully you can kind of guess that like the principles that we're learning, they do build together. Okay. So let's build on what we learned yesterday then. What if I want you to divide? So can I erase this? I want the space. What if I want you to do f divided by g of x? Well, okay. That means that I want you to take x squared plus 4x plus 3, and I want to divide it by x minus 2. Can it? That's a good question, right? Well, this is what I showed you yesterday, right? You might write it something like this real quick. You'd go x minus 2, put a 1, a 4, and a 3 there. You guys still good with this? Drop the 1, bounce, make it a minus 2, subtract to give you 6. That's minus 12. That's not going to work, right? Do these things actually divide nicely? Okay, they might not. There's no guarantee that they do. But if you know your synthetic division, that was a breeze for me just to check real quick, right?
So. Not to be a nitpicker, but the 20-1s can.
Not until Monday. Right. So have them move on to the next question, or if they're buzzing ahead because they're going pretty fast here, maybe give them a quick tutorial on it. I don't know. Okay. That's why though, Scott. It's for Monday. Okay. That makes sense so far? So it means that literally I'm going to have to leave the equation as this then. Like there's nothing more I can do. Like that's where it's left. Okay. Now, this is not considered polynomial. Okay. Our first unit is on stuff called polynomial functions, where it does divide nicely. Our second unit is on non-polynomial functions, where we talk about, well, what if it doesn't divide? So as a general rule of thumb in this first unit, everything will divide nicely. It should, okay? Or the point I want to make is that you discover that it doesn't divide, okay? But we're actually going to focus on what this graph looks like in our second unit. Is that a fair assessment? So if it doesn't actually divide nicely, we'll get to more properties later. But for the most part, we're going to try to find things that actually do divide to start with. So, what if I did the other way around here? What if I flipped it around so that we wrote it this way? Well, then all that happens is x minus 2 divides by x squared plus 4x plus 3. Because all I'm doing is I'm just changing who's the top and who's the bottom of the fraction, right? Now, if you wanted to, you could factor it and say this is x plus 1, this is x plus 3, and this is x minus 2. But is there anything to cancel? So if you stopped here, that's fine. But if you went to here too, that's not unreasonable. And then wouldn't that same kind of logic apply here? You could go with x minus 2 here, and x plus 1, and x plus 3 here. But see how there's nothing on the top and bottom that can cancel? If there's something on the top and bottom that can cancel, like if this and this cancels, then we're back to maybe being a polynomial. But that's not what we had. So that's kind of what my next slide here talks a bit about. Is our unit right now is on polynomial functions. So we're going to focus on things that if they need to be divided, they divide nicely. And we're just talking linear, quadratic, cubic, quartic, quintic. Okay, that's our first unit. After that, we're going to talk about non-polynomial functions like exponential functions, logarithmic functions. I'm pretty sure I taught you guys how to deal with reciprocal, where they have asymptotes. I don't know whether this graph looks familiar from last year, but we'll kind of focus on that, like the graph of 1 over x. But for right now, we're going to do linear, quadratic, constant, I guess, counts. How would you write like a constant function? What does that mean? That'll work, yeah, like x equals a value. And if I asked you how many x's you have, you would say you don't actually have any x's. So it would just be like, sorry, y equals, right, like this one right here is y equals 5. You know what I'm saying? That's a polynomial. It's a really dumb-looking polynomial, but it really is 0x squared, 0x, and 5. But it is a polynomial. You know what I'm saying? Okay, moving on. Okay, let's try doing this one here. Now, this one here should actually divide nicely, because I'm actually going to stick with that from the next little part here. So why don't we try graphing these two things here first? Then we'll see what happens when we try dividing the numbers from each other, and then we'll talk about the equations later. So the first thing I need for us to be able to do is graph this graph and this one right here. And I'm actually okay if we cheat and use our graphing calculators, because like if we do it point by point, it'll take forever. So grab a graphing calculator and use it to help you out. So let's go x squared plus 9x plus 14. I'm actually not going to graph it myself. I'm actually going to use this just for the table of values. And then I'm just going to find some values I can plot. So, like, can you guys get to something like where I'm at my table of values here? And I just scrolled back into the negatives till I found some reasonable numbers here. So here's some value numbers I can plot. Negative 7 gives me 0. Negative 6 gives me negative 4. Negative 5 gives me negative 6. Negative 4 gives me negative 6. Negative 3 gives me negative 4. 2 gives me 0. Negative 1 gives me 6. Can you guys more or less replicate what I did there? I'll just pause for a minute to give you time. Oh, are you doing x's and y's backwards? Okay. Hopefully yours will start looking like mine and you'll see that it looks like a quadratic, right? The other graph, the linear graph, I'm not going to bother typing it in because I'm pretty sure I can rip through the linear one pretty quick. It's going to have a y-intercept of 2, and then it's got a slope of 1. So I'm pretty sure I should just be able to plot it just by hand. Like that. I'm actually not even going to fill in the dots, by the way, because I have colors here. I'm just going to dot them. So if you guys can pull that off, more or less, maybe do something like this. So one's quadratic, one is linear. Anyone want to hazard a guess as to what it's going to look like when you take the quadratic and divide the linear? It should give you a linear, right? Because this is kind of what we learned yesterday, right? This is more or less the factoring concept. One of the factors we believe to be x plus 2. What's the other factor? Can you guys do that without even thinking? Yeah, right? X squared minus 9x plus 14. You need numbers that add to give 9, multiply to give 14. If one of them's 2, the other one's 7. So when we're done, because I'm kind of cheating here, I'm expecting this to be x plus 7 when I'm done. Right? So now let's do it point by point, but now we're dividing. Let's see how this looks. So I'll use a third color now, 1 point at a time. We've got to take the quadratic graph and divide the purple graph. So this right here is the value of 6. And then down here is a value, I believe, of negative 6. 6 divided by negative 6 is good. So red is my quotient. Right, then I've got to go 0 divide by negative 5. 0 divided by negative 5? 0. Now they're both on top of each other. Negative 4 divided by negative 4. This is looking good, right? They're all in a row. Okay, you got to be careful that you do it in the right order. It's the purple for me divided by the green. So I've got to take negative 6 and divide by negative 3. A negative 6 and negative 3 is positive 2, which is good. That keeps going in my row. Okay, don't go too fast here, though, because I've got a point I want to make here. Right here, I'm going to do negative 6 divided by negative 2. That's 3. Still looking good. Then I'm going to do negative 4 divided by negative 1, which is 4. We're still looking good. It's this next one that I want to talk about. What happens when I try to do 0 divided by 0? You can't. It's physically impossible. Right? And so I cannot, there isn't a dot here. I can't use a dot there. There's actually a gap in the graph. And I'm going to talk about that in a second. I'm going to do one more here, though. Right here, I'm supposed to do 5 divided by, or 6 divided by 1. So I believe there would have been a dot right here. But the point I want to make is that right here, there is not a dot there. Is that clear? The reason why there's not a dot there is that I can't use that point because 0 doesn't divide by 0. Now, minus that like missing dot on the graph, wouldn't you guys agree, though, that this is a linear function? And if I kept it going, wouldn't the y-intercept have been at 7? Which means that the graph of x plus 7 totally makes sense. But it's not the graph of x plus 7. It's the graph of x plus 7 with a hole. Does that make sense? It's the graph of x plus 7 with a hole. There was a slide in yesterday's notes. Don't try to find the notes. I'll just find you the slide here, where I actually talked about this, but I didn't actually mention it to the whole group because this would have been way over the 20-ones because they don't know as much as you guys do yet. It's right here. If two functions do divide evenly, it remains a polynomial function, and it has what's called a point of discontinuity, which is a fancy word for there's a hole in the graph. All of this works, but there's just a little spot right here where like your calculator gets an error. Grab your calculators and just type in this, 3 divided by 0. What does your calculator tell you? But what's the error code? Divide by 0, right? Dividing by 0, you guys learned at one point, is like the cardinal rule in math we can't do, right? And so if you're trying to divide by 0, you can't. So it means you have to leave a gap there. That's why we call it a point of discontinuity. So if we were to draw this graph properly, here's how that would look. Let me find where we were again, though. you would actually draw everything in as though it's like a linear function. You would like draw it in, but what you do is where there's the problem, you draw an open circle. And like you kind of like erase. Oh, it's too big of an eraser. You draw an open circle. And that open circle is called, if you want to write it, it's on the next slide, isn't it? Yeah, it is. The open circle there is called a point of discontinuity. Why don't I actually just look at the next slide here, because this is going to talk about what I want anyways here. Okay. So let me just read what I have written. You guys can follow along here. Recall that the denominator of a fraction can never equal 0. Right? And you guys, we talked about asymptotes at some point before, right? Where the bottom of the fraction can't be a 0. Let me go back to the one that's right above you, because you don't have to flip pages here. What I really asked you to do here was take x squared plus 9x plus 14 and try to divide it by x plus 2. What number can this x right here not be? Negative 2. X can't be negative 2, because then the bottom is 0. You get the point here? You're right about the 0, but in order for the bottom to be 0, x cannot be negative 2, which is why right here on my negative 2 line, I had to put a hole there. I literally had to draw a hole and say, this is not physically possible. Which, if I go down to this slide right here, look at the graph that I drew right here. X squared minus 1 over x minus 1. What's the one value for x that you can't use on the bottom? 1. Right? So you can see that right here where x is 1, there is a hole in the graph. Okay, so this is how you would draw that. That makes sense? Okay, I want to show you a common fallacy kids make, or a mistake they make on their calculators, so that you don't do this, hopefully. Sometimes what kids will do is they'll try to graph it, and they'll do it all in one fell swoop. They'd go like x squared plus 9x, what was it, plus 14, I think it was? And then they'll divide by x plus 2. And they'll just try to type that in all in one swoop. This is actually not a bad idea. You just have to be aware of what's happening. If I were to graph this, it looks like the linear graph I expected. But your calculator is not going to like draw a hole in it and put a little arrow there to point it out for you. You know what I mean? Your calculator, there is a hole in that graph right there. You just can't see it because the pixel size is like wrong. Right? If I were to go to my table of values, check this out. 0, 1, 2, 3, 4, error 6. Right? The table of values will show you the hole in the graph. But if you were just to look at it, you're never going to look at the graph and be like, oh, look, there's a hole there. You know what I mean? So if you ever do want to type this in your graphing calculator, just be aware that it doesn't show you holes. Sound good? I've tried that before. Sometimes, depending on the calculator, you can kind of see a gap where all of a sudden it just leaves a little gap there. I have to point one thing out. The value, like if I went calculate the value, hang on a second. If I tried to calculate the value when x is negative 2, literally it'll say y equals, and it'll leave it a blank because it can't. But if I tried doing the value of negative 2.00001, which is like super, super close to it, now there actually is a value. You know what I'm saying there? Because like 2.00001 doesn't make the bottom of the fraction 0. So like really what ends up happening is everything fits except for just one number, right? 1.9 works. 1.99999 works. But 2.0 repeated infinitely, that's the only number that doesn't work. You know what I mean? Like 2.0, 1,000 zeros, then a 1, that would actually work. So, I don't know, you could try your calculator. But I don't think it really serves much purpose, right? Like, it would be a waste of time just to keep zooming in over and over again to hope to find the hole. So, I need you guys to be smarter than your calculators and be aware that when you divide functions, there could be a hole in the graph, and this is how we draw it. So I think I've made the point I need to. So, okay, let's try it a little bit faster, though, because I've been slowing down a bit. How much do I have left again? Okay, good. We're going to finish. Let's try doing this one here. X squared plus 9x plus 8. And we're going to divide it by x plus 2. Now, rather than doing it point by point, though, let's try a different strategy here. What if I wrote it like this? X squared plus 9x plus 8 over x plus 2. Does that make sense how I wrote it there? What is the one number we can't use? negative 2, right? Hopefully we're all in agreement we can't use negative 2. However, this one's going to be the other example. This does not divide nicely, right? If I were to factor it, it actually factors to x plus 8 and x plus 1 over x plus 2. Right? That's what it factors to. Does something cancel? No. Whereas in the last one here, I don't know that I ever wrote it out here, but we could have written this as x plus 7, x plus 2 divided by x plus 2. Can you guys see how the x plus 2's would have canceled, leaving you the x plus 7? That's now polynomial. Take the 2. If they divide evenly, it's still polynomial. But in this example right here, when I try to do this, if I try to do it by factoring, even if I tried to go x plus 2 synthetically divided into a 1, 9, 8, see how like that doesn't work for me? Okay. If it doesn't synthetically divide nicely or factor nicely, this is now considered a non-polynomial function. And so I don't want to spend more than just this slide on it. We're getting to that in the second unit. I just want to show you what it looks like so that you can see a picture of the graph. So I actually want to do it in a calculator though. So go to y equals and type in something like this. Just make sure you put it in brackets. So go x squared plus 9x plus 8 in brackets, and then divide it by x plus 2 also in brackets. I just want to show you what the graph looks like, just so that if this does come up, you'll know, whoa, hang on, this wasn't polynomial. Hopefully your calculator looks somewhat like mine. If you have a newer calculator, you don't get the line right here. Okay, on my older calculator, yeah, you have one of those too. It goes all the way across. Like the graph is actually supposed to look like this. It's supposed to go up like this. Then it pauses, it breaks. It comes at the bottom again and does that. That's what this graph is supposed to look like. And right here, right through the middle of the graph, is that. Do you guys remember what we call that? An asymptote, yeah. Yeah. So when we do this in our non-polynomial functions, I'll talk with you more about the properties of this graph and the asymptote that's there. But I want to make sure you're aware that this is the other possibility. So it either divides nicely, and like if you take a cubic and divide a linear, you get quadratic. If you take a quadratic and divide a linear, you get a linear. You know, that sort of stuff. But you may also get things that don't divide nicely. If they don't divide nicely, you're usually getting an asymptote. Yep. Sorry. Did that make sense? I don't actually think we need to go through and actually graph this thing. I just wanted to make the point of what it looks like. So let's try this example here then. What do you think? Will this end up being polynomial when we're done or rational when we're done? Well, here's one option. Let's try factoring it. Let's see what happens. Can you factor x squared plus x minus 20? So rational means that it's still in fractional form. Polynomial means that it actually did divide nicely. Should I say that one more time? A rational function is what we're going to do later. And rationals mean they didn't divide nicely. Polynomial means they did divide nicely. They just have holes in them. So this guy breaks up into x. Ooh, that's not the right pen. This will be x plus 5 and x minus 4. And then on the bottom, it'll be x minus 6 and x plus 3. Will the tops and bottoms... You guys remember doing this unit in math last year, right? Where we did a ton of stuff. If it canceled like this, and you were just left with this guy on the top, it's a polynomial. But if you're left with like a over b times c, this is not our unit yet. So this one right here is not what we're talking about then. Okay. If you wanted to, by the way, you could try long dividing these. Not that I'd expect you to, but since I have a few minutes here, it's not worth, I mean, don't ever do this, but you could try long dividing them just to prove it. So just watch me do this. I'm going to take x squared plus x minus 20, and I'm going to try to long divide out the x squared minus 3x minus 18. Okay. Why wouldn't synthetic division work? It's not a binomial. Synthetic division works great on binomials, where you just have like x minus 3 or x minus 1 or x plus 1. By virtue of this being a trinomial, synthetic division doesn't really work very well. But I can still do long division. How many times do I need x squared to be multiplied to give me x squared? It's a dumb question. It's 1. So I put a 1 here. 1 times x squared would give me x squared. That's good. We want that. 1 times minus 3x would give me minus 3x. And 1 times minus 18 would give me minus 18. But then when I subtract these things here, I didn't end up with 0. So clearly they didn't divide nicely. Does that make sense? So I just wanted to point that out. You guys can actually synthetically divide anything you want. Or long divide anything you want. I don't know that you necessarily want to, because it sucks, but you could try. Okay, let's do one last example then. Why don't I have you guys try this? We've talked about how to do things from the beginning of class in equation format and in table of values format. Why don't we see what this graph looks like here by just dividing them point by point? So just make sure you do them in the right order though, right? Take the blue graph and divide it by the red graph. And just let's see what the graph looks like. So we've got 5 divided by negative 7, which is negative 5 over 7. We've got 4 divided by negative 6, which is somewhere around here too. I've got 3 divided by negative 5. Yeah. 4. Oh, here's actually a nice one. Negative 4 divides by 2 to give me negative 2. That one actually was nice.
Were the other ones half?
Well, they were like about a half. I just kind of guesstimated where they went. I'm going to use a new color here, though. Because I got negative 4 divided by 2 for negative 2. This is 5 over 3. 5 over 3 goes about there, I guess. Sorry, I didn't put that in a good spot. What else do we got here? This was 6 over 4. 6 over 4 is 1.5? 6 over 4. Yeah, that's negative like 1.5. That's around here somewhere. 7 over 5. Somewhere around there. Okay, let me go this way here. What is 3? This one we can do. What's negative 3 divided by 1? Still negative 3. Here's the real key one. What is negative 2 divided by 0? You can't do that. So I've got the graph more or less looking kind of like this over here to some degree. Shoot. Okay, that's why I'm screwed up here. I'm sorry, guys. I was doing red divided by blue. The one thing I told you not to do. Okay, just watch me do it, okay? Since I screwed you up, this is my fault. Just watch me do it. I just want to make the point. 5 over negative 7 would be negative 5 over 7. That's about right here. 4 over 6, that's 2/3. Right? 4 over 6 is 2/3. I'll put that about here. 3 and 5 will be 3/5. Somewhere in here again. 2 divided by 4 is a half. 1 divided by 3 is a third. 0 divided by 2 is 0. Negative 1 divided by negative 1 is 1. Here's the big one this time now. Negative 2 divided by 0, I can't do. And if I go one step further over here, okay, which way do I need to do it again here? Negative 3 divided by 1 would be negative 3. If I were to draw this graph out, it actually looks something like this and like this, if I finished it off. What's going to happen right here? Yeah, that was the point I think I needed to make on this one here, is that this would have been a good example of something that would have created an asymptote. I could see that by dividing them point by point, but I can also see that by knowing how they're going to look when I divide their equations. The f of x equation would have been x plus 1. The g of x equation would have been negative x minus 3. Would these things actually divide by each other? No. Right? Which is why this is, again, I've said this a lot, but we're going to focus on those graphs in the next unit. So that's going to be all I really touch on them for right now. I need you guys to be aware that they exist. So, okay, let me do a quick recap. We did a lot of different small little exercises to try to just help show little points, but I think at the end of the day, so long as you can go back to my first slide here and do the three, where are they here? The three things. Can you add and subtract a graph? Can you add and subtract an equation? Can you add and subtract a table of values? Can you do that, right, in different ways? Then you're good. Okay.
Brandon Cotton, Jerome Greer, Lydia Nelson, Luna Kim, Abby Wolf, Monia Horta, Michelle Barnes, Cassie Delver, Elizabeth Moore, and Carly Coates. Can you please come to the office for important messages? Also a reminder, it is meet the staff tonight from 5 to 7.
I'm Chris.
So bring your families and have a burger.
You guys coming tonight? It's free food. I'm going to have no one to talk to then. Okay, let me show you guys your assignment a little bit, and then you guys can take off, because it's been a long day here. Here's some of the first questions. You guys should now have the skills to do this. For example, question A, I want you to tell me what h of x is. H of x basically means take f and subtract g. Okay. So, take 2 and subtract 1. 1. Take 5 and subtract 4. 1. Here's how you can answer that, by the way. I just need to snap this into a document. So what you could say is that for x and for h of x, if you have x is 0, what happens when you subtract these two things? It gives you 1. Whereas when x is 5, 4 minus 2 gives you 2. You get how that works there? And then for the next one, you do the exact same thing. Maybe you have to make a table of values for j of x. And so when x is 0, 2 divided by 1 is 2. Whereas when it's 5, 4 divided by 2 actually is also 2. See what I mean there? So that's all we're asking you to do on a question like that. The next question here, I want you to sketch a graph. And I want you to kind of show me how x plus 2 is one graph. F of x plus g is this graph. I want you to work backwards and find out if f by itself is x plus 2, and the graph where it's been added to is this one right here, can you tell me what the missing piece would have been so that this one plus this one would have given you that one? You guys kind of see how the puzzle works there? I lost you there.
I really don't.
Okay, let me write this a little differently then. Subtraction.
Oh, subtraction. They don't see it either. I'm wrong.
Okay, so what I'm telling you is that f of x is x plus 2. I'm telling you that if you took f of x and you added it to g of x, it would give you x squared plus x plus 6. So really the question is, if you needed to add a g of x, so that when you added them you got to this, what would the g of x need to be? You kind of see how that works? So, I'm still missing there? Well, let's do it together as a group here.
Oh, sorry.
Okay. You want to end up with an x squared. This one doesn't provide an x squared, so you'll need an x squared.
Algebra it?
Yeah.
Okay.
Yeah, basically algebra it. Okay. Okay, for the third question here, can you leave the third question until Monday? I have to tell you how this notation here works. So leave that one for now, if you get that far. You could start doing some of these ones here. The way this one would work, it's a little bit of a different setup. Here, if I have 1, it gives you 1. And over here, if I have 1, it gives you 2. You guys see how they're a little bit offset, though. Here, 1 gives 1, and here, 1 gives 2. What happens if I want you to subtract them? What would 1 then give? Yes. Darian, you have it. Let me write this out here. Okay. if f minus g, here 1 gives 1, and here 1 gives 2, but I want you to subtract them. So what will 1 give? Well, this 1 minus that 2 will give you negative 1. See how I'm kind of writing that there? Pick another value. Here, 2 gives 3. 2 also can give negative 4. When you subtract them, what do you get? Say it? Yeah. Okay. Here, 0 can give 3. But do you see how over here there isn't a 0 to start with? Well, if this one doesn't have a 0 to start with, and this one here does have a 0, you can't take something and add it to one that doesn't exist. You know what I'm saying there? So, like, you wouldn't have 0 comma something because there's not two numbers to add, so like you just leave that. Because you're not adding 0 to it, you're adding, I don't want to say nothing to it, because nothing means 0, right? But you're taking a number and you're not adding anything to it. You're not adding 0 to it, you're just not adding to it. So there's an error there. You know what I'm saying? Does that give you something to work on? So try dabbling in this with whatever time you get tomorrow, because I know tomorrow's kind of a crazy day. And then Monday, we're going to do one final lesson on this stuff. And then Tuesday, I'm going to give you a work day. Okay? And I'm pretty confident that you guys will be able to finish this all in just one hard day of work. So. Okay, thanks, guys. You can take off. We'll see you later.